Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and congratulations if you made it this far to the Chapter 2 review in the Integrated Math 2 Big Ideas Math textbook, assuming that you've learned sections 2.1 to 2.8 from adding and subtracting polynomials to learning their names of them, multiplying polynomials with special cases, getting the GCF and zero product property, factoring basic quadratic trinomials, factoring a more advanced quadratic trinomials, factoring special cases, and factoring polynomials completely, including factoring by grouping. Wow, that's a whole bunch of them, of 8 sections worth of work. A lot of drill and kill problems, not really much of any graphing except for looking at intercepts, which will be great for the next chapter. But now we go to the review. 41 questions of review with examples leading up to them. I'll make sure to look at what they put for those examples and we'll do those problems. Now you're in the future, so you know more about how long this video is than I know right now. But if you go down the description section down below, you'll see not only a playlist for the Big Ideas Math textbook solution guide videos that I have, but you'll also see timestamps to the sections of the problems for which I'll be covering for you guys here for each section as they go in order. So we start with we start with adding and subtracting polynomials and naming them, and then we go to distributing, and then the big chunk on factoring. I haven't seen the problems before, and I'm sure they're going to hit some word problems along the way. So let's go ahead and take a look at what we are going to get started with. In section 2.1, adding and subtracting polynomials. Now what they show you in this first set, when you find this difference of this polynomial minus this polynomial, and by the way, they write each of them individually in standard form to remind you descending order of degree. This is a degree 3 term, degree 2 and degree 1, and a degree 3 term, degree 2 and degree 1. We are going to combine like terms, but in order to do that, we have to first get these things out of these parentheses, not by distribution and multiplication like of all the terms, no, because there's subtraction in between. You subtract this term, you subtract this term, you subtract this term. When you end up subtracting all 3 terms like that, their signs end up changing. All of these were negatives, and they end up now being positive. Now they kind of write it differently. They keep them in the parentheses. That's fine. I tend to rewrite it without parentheses. You'll see what happens. And then they regroup the terms so that you can combine like terms. X cubes will combine together. 2x cubed plus 3x cubed. And then 6x squared plus 2x squared and negative x plus 9x combined. You add the coefficients. They keep the exponents the same as you're combining like terms. 2 plus 3 is 5. X cubed, 6 plus 2 is 8. X squared and negative 1 plus 9 is 8x. Written in standard form as a final answer. So we're going to go with our problem set. They're going to ask us to do a little bit more than that, but that's just but one example of what they had. And by the way, that would be known as a cubic trinomial. It's degree 3, a leading coefficient of 5. I think that's all I'd want to say about that. So let's go and look at the problem set that they have for us. We are going to rewrite the polynomial in standard form, 6 plus 2x squared. Its standard form takes the degree of each term, a constant is degree 0, and a quadratic is degree 2, and rewrite them so that it is highest degree to lowest degree, 2x squared plus 6x. That's our first thing asked. We are also going to be identifying the degree of the polynomial. The degree of the polynomial is the same as the degree of the leading term. It is 2. No, you do not add all of the degrees of each term together, even though 2 plus 0 is still 2. Even if this was a 1, the degree would still be 2. I don't know if I should be boxing these other things here. Oh my gosh, that was a lot that I got rid of. Let's do that. There we go. Okay. The leading coefficient is the coefficient of the leading term. By the way, when I keep saying leading term, it's not from what they wrote, it's from what standard form is. So the leading term is, leading coefficient is not 6, but it's 2 because of this guy. And classify by the number of terms. I'm going to do you one better. I'm also going to classify by the degree. So the name of this polynomial, it is it is degree 2, which makes it a quadratic. That's the part that the book didn't actually mention, but what they also wanted was by the number of terms. Because there are 2 terms, it is a binomial. So it's a quadratic binomial. And that's number 1. Numbers 2, 3, and 4 are a lot more of the same. Let's continue forward. No real work to be shown outside of rewriting this in standard form. And of course, standard form seems to answer a lot about this stuff. By the way, standard form is expected the rest of the way whenever we do these problems. If you've noticed with factoring, as you've done it before, standard form's kind of a nice crucial way of showing how to factor based on your leading stuff. So just keep that in mind. This is degree 3, degree 6, and degree 0. Let's get the degree 6 term first, and then degree 3, and then degree 0. You'll notice that the coefficients have absolutely no impact on how you order them. It's all about the degree of the individual terms. The degree of the polynomial is 6, as the leading term is of degree 6. Its leading coefficient, based on that, 5p to the 6, is a 5. The name of this polynomial is 6th degree trinomial. I believe also called a sextic trinomial, but I think after about 4th degree quartic or 5th degree quintic, at that part, names are less known, less common, or less expected for you to actually know. But trinomial because it has 3 terms. Of course, the book's only asking for the number of terms for a name. I would want a little bit more. Number 3. We have 9x to the 7th minus 6x squared plus 13x to the 5th. Now, by standard form, the first term, this is degree 7, 2, and 5, so the first term is still going to be 9x to the 7th power. The 13x to the 5th will go next because that is of degree 5, and negative 6x squared, that is of degree 2. So there's your standard form. The degree, like I said, is 7. I don't know, is that a heptic? See, that's hectic for all I know. It's very hectic. I don't actually know what it's actually named. That's why I'm going to call it 7th degree. But the leading coefficient is 9, positive 9. And the name, it is a 7th degree trinomial. So based on the degree and number of terms, and if you don't know the name of it, at least say that, like that. And then number 4. Negative 12y plus 8y cubed. By the way, none of these were, but if they were already in standard form, don't try and, let the problem trick you too much. Just rewrite exactly what they gave you. Now, this is not in standard form. Negative 12y, that's degree 1, y to the first power. 8y cubed, degree 3. What am I looking for first? The standard form. So standard form, we need positive 8y cubed minus 12y. That looks good. I see a GCF, but I'm not going to get that. The degree of this is degree 3. The leading coefficient is positive 8. Remember, it's not the entire term, it's just the number. And then the name, this is a cubic, degree 3, and binomial. They didn't show up here, not in the notes or anything else, but a 1 degree term would be a monomial. A 4 degree term would be a quadrinomial. A 0 degree I said term, a polynomial. A 0 degree polynomial would be a constant. A 1 degree is linear, 2 is quadratic, 3 is cubic, 4 is quartic, and all that. All right, numbers 5 through 8, we are going to find the sum or difference. This is kind of like what the example showed above. I'm not saying I do things differently per se, but my first aim is to kind of get rid of parentheses. I will combine like terms by finding terms that are alike, but not necessarily rearranging them either. Now, when you have addition of this binomial and this binomial, both linear binomials by name, the addition isn't actually changing or affecting anything within these sets. The parentheses are there more so for show than anything else. 3a plus 7 is still exactly that, being multiplied by 1, plus this being multiplied by 1, plus a minus 1. So you add the positive, you add the negative. It becomes addition and subtraction. It's basically written the same as without it. But I want to get rid of the parentheses first just to see the signs for what they truly are. Nothing else in the way. Now when I combine like terms, 3a plus 1a will combine to be 4a, not 4a squared. How many a's are adding? That's the answer, 4. And 7 minus 1 is 6. And I'm always going to write those in standard form. So we have 4a plus 6. Also a linear binomial, if they asked us. Number 6. And like I said, they seem to present most of these in standard form already. So if I just maintain the form and say, let's find my x squared terms first, like I'm going to say, then we'll do that. X squared plus 6x minus 5, a factorable quadratic trinomial, actually. Plus 2x squared plus 15, though we're not factoring. And also notice, we're not foiling or whatever, guys, right? We're not doing this distribution thing. No. It's not. This is addition, not multiplication. So we're just adding. Same thing as last time, just rewrite them without the parentheses. Really, really big bit. You might be wondering if this seems like a redundant step. A little bit for addition, but not for subtraction, right? So when we hit a subtraction problem, we'll see. Anyway, I'll start with the x squared terms as it's in standard form. 1x squared plus 2x squared is 3x squared. 6x doesn't seem to combine with anything, so I get a plus 6x next, and negative 5 plus 15 is positive 10. And there is that guy there. I don't believe that would be factorable. Not that they're asking us. That is a quadratic trinomial. Let's move on to number 7, and I need another page of binder paper. Let's flip it over. Number 7, we get negative y squared plus y plus 2 as one quantity. And this time we will subtract. We're going to subtract y squared, negative 5y, and negative 2. Notice how I said we will be subtracting all three of those. So this first guy is not affected by that subtraction. It's just a 1 times this. These signs still stay the same. No change there. However, these next three do get affected, and all three terms. Subtract a positive, you get negative y squared. Subtract this negative 5y, and you get positive 5y. And subtract the negative 2, and you get plus 2. So that's where you get the effect that's a little bit different. You now see them for what they are. Nothing else anymore. I don't see the subtraction for what it is. Now all the signs are what I need them to be. Negative y squared minus y squared, negative 1 minus 1 is negative 2. So we get a negative 2y squared. Y plus 5y is 6y, and 2 plus 2 is 4. If anything did cancel and become 0, then you don't need it. That's another quadratic trinomial. However, and then number 8, last subtraction, we have p plus 7 minus 6p squared plus 13p in parentheses. So quantity p plus 7 minus quantity 6p squared plus 13p. So p plus 7 is exactly that. Now we get to distribute this negative here, and both of these will turn into subtraction. Negative 6p squared minus 13p. And the hush-hush around here is we imply we should get standard form within our answer, which is exactly what I'm going to do and what I want. So I'm going to start with not combining p and negative 30. I mean, you can, but I'm going to find my highest degree term, and that's degree 2. So the p squared does not combine with anything. I'll start with that. Then we'll go to the p terms. P minus 13p is negative 12p, and 7 doesn't combine at all either. That's plus 7. Another quadratic trinomial to finish that off. A couple things with leading negatives to remind you when we hit factoring that we will factor out that leading negative if it exists once we're in standard form. Okay, before we hit number 9, let's look at what multiplying polynomials is all about, something that people actually are sometimes better off with than the adding and subtracting of polynomials because reasons. I guess the word FOIL really helps them out in some way. I'm not really sure. Now you don't see the FOIL. You don't see the word FOIL on the screen, although the book talks about it. This is a case of foiling when you have a binomial times a binomial multiplying the first terms x times x. They're showing a version of this for distribution. It works out, but you see x times x there. That would be the f of FOIL. So I got to use my mouse on this side here. And then the outer terms. Sometimes I say outside. X times negative 9 would be the outer terms to multiply. The inner or inside terms, 7 times x, that's I, and L, caps off FOIL for last, 7 multiplies with negative 9, and you add the results of all four things. That's how distribution in a nutshell works. Under addition and subtraction, you just multiply each individual part that we're already being added, and you still add them. So that's that FOIL concept, and x times x is x squared. Any x's that multiply together raise the degree, that multiply together. Not that add, but that multiply. Negative 9x comes here, 7x, and negative 63. And then you get to combine the two middle terms, leave it in standard form, or get it in standard form if it wasn't there. That's just but one example. Let's try another one ourselves with x plus 6 times x minus 4 on number 9. As far as foiling goes, I'm not going to write the letters, but I'm going to start with the first terms, multiply those together, and you get x squared from x times x. X times negative 4 is a negative 4x plus 6x. And then 6 times negative 4, not 6 minus 4. Remember, everything is multiplied. 6x means 6 times x, and 6 times negative 4 means negative 24. The two inside terms combined, this happens quite often when you are doing these with a linear times a linear binomial. Some of them don't show up in that way, and that's totally fine. A lot of these I skip that inner step because I understand what I'm doing from the outside and the inside. And as I move further into my review, once I start hitting the factoring in section 2.6, you are going to have to keep up to my speed, or pause the video, slow it down, or not watch it. You're going to have to keep up with my speed when it comes to me doing that foiling. I'll go straight into saying negative 4x plus 6x. like that kind of idea. And so I might speed up here in a little bit just so you're aware. In terms of combining. Number 10, we have y minus 5 times 3y plus 8. And once again, the same thing happens with FOIL. Y times 3y, generally I like this one first with the 3, but that's okay. Y times 3y gives us 3y squared. Y times 8 gives us 8y. Negative 5 times 3y gives us negative 15y. Negative 5 times negative 8 is negative 40. So again, we got 8y minus 15y, which will combine. And those will combine to negative 7y. So 3y squared first, negative 7y second, and negative 40 third. And keep in mind, this would factor back to this, something that we get to practice later. But that's the multiplication distribution. Number 41, number 11. I wish I was on number 41. It'd be the last problem. Number 11. We have x plus 4 times x squared plus 7x. Again, they make it really hard for me because I like to get this one written first, but that's okay. We got x cubed when we multiply those two. Now, generally, x times x squared or x times x, people have no problem raising the degree. But I'm just going to warn you right now when we hit some other problems, you might have trouble with it because you might forget to increase the x things. You're more focused on multiplying the numbers than these, but when there aren't any numbers, I think you make more sense of it. X times 7x is 7x squared, 4 times x squared is 4x squared, and 4 times 7x is 28x. X squared terms combined, these seem to have an extra degree in all of them. Now we get a cubic trinomial where we now get 11x squared here and plus 28x. So maybe I'm going a little faster with these than normally expected, but I don't expect this is your first time you're seeing these. I said congratulations on making it this far. Now you're maybe just revisiting this for the first time after doing a lot of factoring. However, if you did factoring with me, we did a lot of foiling in the process anyway. Now this last one is number 12 is not foiling because you have a 2 by 3, 2 terms by 3 terms. And there are two different ways I'll go about doing this problem. The first way through that common distribution, but not FOIL, because FOIL means first, outer, inner, and last, and you seem to skip the negative y in the process. You got to multiply each term in one polynomial by every term in the other polynomial, by the other quantity. So negative 3y multiplies with all three of these, and 1 multiplies with all three of these. And 1's very easy to multiply by. The numbers don't change, so that's good. But negative 3y times 4y squared, here's what people tend to commonly write, negative 12y squared. But it's not squared because y multiplied with it. See, we did x times x squared and we got x cubed. People will generally be okay with that. But this guy right here, y times y squared, it also becomes y cubed. Don't forget with that y being there. Furthermore, if nothing in here combined before, then after distributing something through, nothing here should still be able to combine. And I bring that up because if you kept that as a y squared and there was another y squared here, then you're combining something that shouldn't have been able to in the first place. So there's that. Negative 3y times negative y, that'll be positive 3y squared, right? Not just positive 3y. And oftentimes, through multiplication, I've been seeing this from my students. Sometimes, negative 3 minus 1 is negative 4, and, you are multiplying. Right? Everything here is multiplying. Negative 3 times negative 7 is positive 21, and we'll put the y in, and you get a y. So if you notice, no three of these combined, right? This isn't a y squared and a y where these suddenly combine when they didn't before. They still shouldn't. 1 times 4y squared is 4y squared. All of these will be the same now. Negative y and negative 7. So now the 1 multiplied through all three of those terms. And a 2 by 3 should leave you with 6 terms before we combine. So now as I combine like terms, I will get, this is a first term that doesn't combine with anything, so negative 12y cubed. Now 3y squared adds with 4y squared to get 7y squared. 21y minus 1y, it's not 21. You don't eliminate the y's, it's 20y. Again, I'm kind of stating the things that I would see from a student. And then the minus 7 doesn't combine with anything there. Now, I said I'd do the problem in two different ways. The only alternative that I wanted to present to you is kind of working off of that like rectangle, that box method, if you will, where you make a 2 by 3 construction with your terms on the outside kind of representing the base and height of something which you come up with an area of, like negative 3y plus 1. And then 4y squared minus y minus 7 like this. And then you multiply them individually into here. That construction seems to make more sense when you hit 2 by 3, 3 by 3, 3 by 4, stuff like that, because this can get a little long, messy, a little arduous. It's the same amount of stuff. I still get negative 12y cubed and the like, but perhaps, maybe, just maybe, it gets you to remember the negatives. It gets you to remember the multiplication. A lot of things here can assist people that maybe did not before, and it's nothing I would ever force on a student. It is exactly the same thing as what you have here. And sometimes there's a layout where you'll see like these terms combine and these terms combine, but the end goal is we find the area of this rectangle, which means we add up these individual boxes together to find them, so you still combine like terms and you still get that answer. It's just another layout, another organization tactic, and that is it. And the book talks about it too. I think they call it the table method. All right, that was section 2.2. Now let's move on to section 2.3. And 2.3 is a version of 2.2, but it includes what are called special cases. Now, special cases are exactly as such because they all present themselves in the same way, and you can work off that speed a lot better to distribute. I can say all 4 of these answers off the bat really fast for you right now. But you know, x squared minus 81, 4y squared minus 16, p squared plus 8p plus 16, and 4d squared minus 4d plus 1. Boom, I got them based on the concept of what the special case thing gives you. I didn't have to FOIL. What they do is what they do. So there is the squared binomial pattern, which when you square it, you don't end up just squaring the 2 individual pieces. Yes, that's a part of it. You can see that 6x is squared and 4y is squared, but there's a middle term, and I call it middle term based on just standard form basis. There is a term in between that you double the product of those 2 terms, the 6x and the 4y. And the concept is when you square something, multiply it by itself, the foiling would have brought you there. It would have been 6x times 6x to get the first term. And this is the combination of outer and inner. It's 6x times 4y plus 6x times 4y. Adding something to itself doubles it. And then the 4y squared is 4y times 4y, the 2 last terms. And you combine like terms and you get this big guy right here, which we want to recognize over time. These are perfect square trinomials for factoring's sake. It makes factoring these a whole lot easier. The last one here is what's called a difference of 2 squares result from adding a sum and difference pattern. You have something plus something, like a plus b times a minus b. The b sign changes, the a sign stays the same, whatever it was. And what ends up happening here is, through FOIL, first terms multiply. Last terms do multiply, but those outer and inner terms, this plus this, they are exact opposite signs of each other. Here I'd have negative 6xy plus 6xy, and they'd cancel out. So there is no middle term. Whereas this would double up and have it, this would have none. So you end up only squaring the first term and last term. That's why it's called a difference of 2 squares. First term squared minus last term squared. And that's what we begin with on number 13. So number 13, we have x plus 9 times x minus 9. Going straight into the special case recognition of the sum and difference pattern being a difference of 2 squares. We square the first term, we square the last term, we subtract the result. X squared is exactly that. That is x squared. 9 squared is 81, and you subtract those 2 because the middle 2 terms, negative 9x plus 9x, are gone. And yes, I'm squaring 9, not saying, oh, it was negative and you square it, it turns positive. No, 9 times negative 9 is negative 81. We're only squaring the 9 and subtracting that result. That's what we get from it. Let's move on to number 14. We have another difference of 2 squares. Sum and difference pattern, but another difference of 2 squares result. 2y plus 4 times 2y minus 4. Now, the in-between step isn't really a required step. I think it's more for you to just have knowledge of what's actually happening, recognize the pattern, spell it out. A squared, whoops, I just wrote that wrong. A squared minus b squared, like that. Now, squaring 2y, the quantity, means you square the 2 and you square the y. 2y times 2y is 4y squared. 4 squared is 16, which we're subtracting that. That is standard form. 4y squared minus 16 is the result to number 14. I'll just pause on that so you can just digest that. Now the next two, numbers 15 and 16, let's see where we go from here. This is no longer a sum or difference of 2 squares by any means. Instead, this is a perfect square trinomial. I wrote the problem wrong. This is a perfect square trinomial that we get as a result of squaring a sum or a difference. Square of a binomial pattern. So p plus 4 quantity squared means we will be squaring that first term and last term, but in between here, we will be doubling the product of p times 4. We will be doubling 4p. 4p doubled is 8p, so this becomes p squared plus 8p plus 16. And I know for some people you still see this and wonder why we're doing it this way. If you heard me at the very beginning, hopefully you saw how fast I said them. That's why, because you can calculate these by recognizing its pattern, not needing to write this inner part if you know exactly what's going on. But I'm spelling it out for you. You're practicing some of it. It's study material. This is for you to understand through that. But also, better yet, it really helps when you hit factoring. -1 plus 2d quantity squared. I mean, it's not in standard form to begin with, and if I wrote it in standard form, this would look so much better as a problem. This would be 2d minus 1 quantity squared, so I already want to get into that. Maybe this time I won't put in the in-between step. Let's try this. We saw that 2y quantity squared was 4y squared, so 2d quantity squared would be 4d squared, indeed. Now let's double 2d times -1. Let's double -2d. That's -4d. And then let's square 1, or -1. Either way, that's a 1. So the difference between the difference of two squares last term and the perfect square trinomial last term is the difference of two squares final term will always be subtracted. Remember what it comes from, a positive times a negative. The sum of two squares result, keep in mind what that comes from, a positive times a positive or a negative times a negative, 4 times 4, and in this case here, a negative 1 times -1, a negative times a negative. So the last term is always added. That's why I said it doesn't matter whether you square positive or -1 or call it. But notice how this term got subtracted. I doubled the product of 2d and -1, or I'm subtracting the product of 2d and 1 when there's a minus there. So there will be one term that will be negative. And that is section 2.3. Okay, now we move on to the factoring bits and zero product property. And they lead you with an example of zero product property to go straight into it for the example leading to numbers 17 and 20. They begin with this example here. We solve x plus 6 minus x times x minus 8 equals 0. Notice that this is a factored form set. When something is factored, that means you've created a product. I put a little dot in there just to represent that. We have a times b, and a times b equaling 0. That's just how we say that in zero product property. If a times b equals 0, one of your answers has to be 0, either A or B. If x plus 6 as a quantity equals 0, then x is -6. If x minus 8 equals 0, then x equals 8. Either of these values will give you 0 as a result in this thing. Notice that -6 plus 6 is 0 times -14, if you plug -6, which is 0. And 8 plus 6 is 14 times 8 minus 8, 0. 14 times 0 is still 0. Those are the only two numbers that work. Notice that we weren't foiling in this case. We wanted a product, and when that product's equal to 0, we can solve that easily. They don't start that way always. For these problems, we're going to have the first one not start that way. So the first thing that they don't show you on this first problem is something we're going to see or seek every problem here on out. If it's a polynomial that's not factored, that is simplified, it's in standard form, or not in standard form, first of all, get it in standard form, set it equal to 0. But always seek greatest common factors. Greatest common factors are numbers or variables, including leading negatives, that can divide out of all of your terms, be written on the outside, to create a product. We don't have a zero product property right now. We have a zero sum property. And right now it's all guess and check for us to figure out what it is until I see that both of these share a common factor of x. If I write the in-between step that I generally wouldn't ever write like this, you can see that x is a shared factor in both of these terms. So if I factor x out of both terms, I'm left inside with x plus 5. It's basically an anti-distribution matter. I'm asking x times what would give me x squared, x times what would give me 5x, and that would be it. But what I've just done was I've created a product. This x is multiplying with this x plus 5. Treat that as a single number because PEMDAS says anything in parentheses we treat as a single quantity. So if x times x plus 5 equals 0, either x equals 0 or x plus 5 equals 0. Now x equals 0 is actually one of your solutions right now. I substitute 0 into this original thing, I'm going to get 0 out. But what do I got to substitute in here? Subtract 5 from both sides, and x equals -5. So a method for solving quadratic equations, the only one that we've learned so far, is called solving by factoring. In Chapter 4, we're going to learn at least 3 other methods, and I'm sure that as we graph, we'll understand what it means to solve by graphing a little more so. Even though we've done them in some of our problems together, we haven't graphed. The graph was drawn for us, but we have found roots, x-intercepts, and those are part of what solving by graphing means. but we're solving by factoring right now, or when we're factored, like number 18, 19, and 20. Z plus 3 times z minus 7 equals 0. This is a factored set equal to 0 right now. You want this. We already say if z plus 3 equals 0, I'm going to jump straight into it, subtract 3 from both sides, not x, but z equals negative 3, and add 7 to both sides here, z equals positive 7. No harm in just getting straight into that. If there's one thing I probably should be writing is the word or. You're not going to see me write that a lot. It's just a nature of habit, not doing so. But it's definitely not and. Just make sure you're not putting and I'm sure out loud I'm saying or. Number 19, b plus 13 quantity squared equals 0. If I go back and recap what we were talking about previously when it came to special cases, is that squaring something means multiplying to itself. So although this will feel like a wasted step later, I want to remind you of what it is that we're looking at here. Something times itself. I multiply something times itself to get 0. It's the same solution that we're looking at in the end. Once again, it's a wasted step to write, but b plus 13 is the only thing that can equal 0 in this case. That's not a capital B, by the way. So b equals negative 13. That is the result in the only one solution. There are instances where quadratics will only have one solution or no solutions, although I don't think we're referring to any of those right now. That's not till probably some parts of chapter 3 with our graphs, but more so chapter 4. And then finally, number 20, we have 3 factors. They are already in factored form. Get used to us doing factoring right after this problem, I'm sure, including when it comes to solving or seeking GCFs, such as number 17. But we have 3 factors. 2y, consider that its own thing, boom, times y minus 9 times y plus 4 equals 0. This is no longer a quadratic. And by the way, I said this was a quadratic. You can tell by the squared bit, but also because when you FOIL, you'd get a degree 2 polynomial. If I multiplied all these 3 things out, I'd get a degree 3 polynomial. So this is called a cubic. Cubic should have 3 solutions, or can have up to 3 solutions. If 2y equals 0, then y equals 0. That's one of your solutions. In this case here, y equals 9, add 9 to both sides, just basically flip the signs, and then y equals negative 4. Now, you don't always flip signs. We've so far only seen cases where signs are flipped. I'm surprised they didn't show us anything of the other sorts, but we will run into those where you might have to take 2 steps and show them, because we're trying to find the values that would work for that. Okay, and that is section 2.4 with GCFs, starting with that part. That's really important for anything we have carrying forward. And then, of course, the zero product property solving for these guys, which we will be using for other problems, if they are equations. All right, section 2.5, we have to factor x squared plus 6x minus 27. Give me one second. We have to factor x squared plus 6x minus 27. Now, as we've FOILed, let me go back to some of my problems as that's still on the screen. As we've done FOILing before, you've noticed that that middle term was a combination of 2 terms before. Negative 4x plus 6x was 2x. 8y minus 15y was negative 7y. That kind of deal. That is from a linear binomial times a linear binomial. And where the first thing that we get is that x squared, or in this problem, in this example as well, an x squared. X squared comes from 1x times 1x. Our goal is to take what is right here when we distributed and go in this direction. Our goal is to factor. So x squared comes from some x times x. This trinomial comes from a binomial times a binomial because we need a constant term from these two, and we need a linear term from the sum of what were 2 terms before. Now, those 2 terms happen to be the same 2 numbers that appear in the factorization. You notice negative 4 here. You notice 6 here. Not only that, those 2 numbers obviously multiply to the final term because in FOIL, it's the 2 last terms multiplied. The whole case that I'm making right here is that we're going to play a little guess and check game with our numbers that we have in our problem, such as in this one right here, involving this positive 6 and this negative 27. Noting that the negative 27 is the combination, the product of the last 2 terms that you have in your FOILing bit. Right, those last 2 terms, it's their product. And the 6 is the sum of the 2 terms that happen from the outside multiplied plus the inside multiplied. And as you know, because they're x's in front only, it's just those numbers themselves. What we saw here was 6 minus 4 is 2. Negative 5 plus 8 is, hold on a second, this one's a different kind of problem. I'm going to skip number 10, but 6 minus 4 is 2. This is saved for when we hit section 2.6. Yeah, so there's that. So what are we going to do? We're going to try and find 2 numbers that multiply to make this term and add to make this term, or these values. Now, I've drawn diamond things before, so if you ever see me kind of do that, I'll like do something here where we have a product of negative. I'm not going to do this really outside of this problem, but if you've seen me do it before, I'll put negative 27 as the product, 6 is the sum, and you're trying to test numbers. So notice their test that they give you. Negative 27 and 1 as factors of negative 27 would add to negative 26. Negative 1 and 27 would add to positive 26. I'll tell you why I would never bother testing both of those. Negative 9 times 3 is negative 6, and negative 9 plus 3 is negative 6, and negative 3 plus 9 is positive 6. Now, positive 6 ends up being the value we wanted from these two numbers. So negative 3 and 9 are the two values that we kind of wanted, excuse me, from this result. These are the two values that also appear in your factorization. I know I'm still on the example. The other problems after will go a lot faster. So this factors into x minus 3 times x plus 9. That if I FOIL that back out, I get x squared plus 9x minus 3x minus 27. And 9x minus 3x is 6x. So that's what we're trying to get to, that kind of thing. Now, like I said, I would have never tested this, and I never would have tested this. And the reason is because I needed a positive result, a positive sum. And so I'm only going to test my factors where my larger factor is the positive one, because there's no way I'm going to get a positive 6 out from doing a negative big plus a positive small. That's all I'm going to say. Okay, so I'm going to move on to the problems right here. I think it'll make more sense if it hasn't already made sense in the past. This is the basic level of factorization. Number 21, p squared plus 2p minus 35. Our goal is to factor this thing. I'll do diamond one more time on this. Outside of that, I will not. But I'm trying to find two numbers that multiply to make negative 35 and add to make positive 2. So your factors of 35 are 35 and 1 and 7 and 5. With the negative product and positive sum, like I said before, I would only bother testing with the smaller number negative. 35 minus 1 is 34, but 7 minus 5 is indeed 2. So 7 and negative 5 are the values. That's not the answer, but it's very close to it. That leads me to a p plus 7 times p minus 5 factorization. Once again, foiling this thing out would have given us this, because negative 5p plus 7p is 2p, and the last term we get negative 35. This is really easy when it has just a positive 1 p squared here, because they don't seem to affect the middle terms, but in section 2.6 they will a little more so. We'll get ready for that. Number 22, let's factor b squared plus 18b plus 80. Now we're trying to find two numbers that multiply to make 80 and add to make 18. If you considered factors of 80, try and divide 80 by 1, 2, 3, 4, 5, 6, 7, 8, as much as you can until you list all your factors. So 80 and 1, 80 plus 1 is 81, no. 40 and 2, 40 plus 2 is 42, no. It cannot divide by 3. Divide by 4, you get 20. 20 plus 4 is 24, no. Divided by 5, you get 16. 16 plus 5 is 21, no. Divided by 6, no good. Divided by 7, no good. Divided by 8, you get 10. 10 plus 8 is 18. We needed 18. So 10 and 8 are the two numbers that we wanted. So you get b plus 10 times b plus 8. Now, you might have beaten me to the punch on the problem and if you did, I'll have you know that the instant I read the problem, I also knew the answer myself. So I beat you to the punch. You can't beat me to it. But the point is that, what if it wasn't 18? What if it said 21, right? What if it said 21? Well, you might not have beat me to the punch anymore, because you have to consider all of your factors of it. If you go to more common ones first, and you understand that 80 plus 1 won't give you 18, then just skip the ones that you know that won't work and try the common ones first. I would tend to do the same thing. I probably would have tested this first in my head and gotten that same answer. But make sure you consider all in case that's not it, and know how you can get them. That's the important part. Okay. Next one, z squared minus 4z minus 21. Let's factor that. Factors of 21 that add to, negative 21 that add to negative 4. Notice that because the product's negative, one number will be positive, one will be negative. So we'll try 21 minus 1. Negative 21 plus 1, which is negative 20. And negative 7 plus 3, which is negative 4. So we get z minus 7 times z plus 3. Now, if in fact you've tried all of your factors, you did the math right, and none of them seem to work, that would actually mean that it's not factorable. They're not going to do that on you for these problems, but just make sure that you're aware that that's what it would mean, or you factored as much as you possibly can. And number 24, we have x squared minus 11x plus 28. It should also be noted that in section, these reviews, they are supposedly all-encompassing, but they do but one example in each of these things, and all the problems don't seem to hit everything. For example, in this section, have you noticed that we never used zero product property? Oh, I'm sorry, I guess the part didn't either. But we have to solve these sometimes using, like if this set equals 0, notice how all these factored form things, why do we factor? To then solve z equals 7, z equals -3. Now, they're not asking us to do this here, so don't introduce it if it's not there. You don't solve for anything if it's an expression. But the point of the matter is, these problems didn't introduce them. I'm looking at section 2.6 right now. They're not having you do them there either. So I might show some and say what it looks like. Maybe we can do it for this problem if I put an equals 0 in blue to remind you that this isn't part of the problem, not part of original problem. But it's probably good to note that that's why we're doing it in the first place. And the problems did do them in the original sections. So the fact that the review's not doing it's kind of wish they did. They had 4 problems to do it with. They could have done it with 2 of them. Anyway, finding 2 numbers that multiply to 28 and add to -11. Oh, the other thing I wanted to state was that none of these showed GCFs, but it's worth noting that I would always say, if there's a greatest common factor, you factor it out first. Anyway, x squared minus 11x plus 28, 2 numbers that multiply to 28 that add to -11. Now, positive 28 still means either both positive or both negative. But because the sum is negative, we're looking for 2 negative terms. If you want to just pretend like it's an 11 right now, just add your numbers. That's fine. We'll make sure to turn them negative after. So 28 is 28 and 1, 14 and 2, 7 and 4. 28 plus 1 is 29, 14 plus 2 is 16, 7 plus 4 is 11. So the numbers will be 7 and 4, but in the case of -11, it's -7 and -4. And -7 times -4 is still positive 28. So x minus 7 times x minus 4. That would be the answer. Now, let's say that this was set equal to 0. Your whole goal for these problems to solve for x is factor it. Create a product out of these things. Have it set equal to 0 to then use 0 product property. If x minus 7 equal to 0, then x would equal 7. If x minus 4 equal to 0, then x would equal 4. Once again, not part of the original problem. Let me highlight that even more so just by, like, I don't know what I just did. Just by trying to, there we go. Like, thin it out more. There we go. Okay. Okay, let's move forward. Let's look at section 2.6. Now, I teach it the same way that they do in a general case. They might test a few more numbers than I would bother testing, and I talk about strategies with that. But they talk about basically trying to seek out factors of the first term and factors of the last term and testing them in your foiling process in the way that, this is why I said foiling is kind of nice and important for these problems. And they also write them in a different order than I do. But testing your numbers to see which ones that when you FOIL it out, when you multiply this whole thing out, you actually get the middle term that you're looking for. Case in point of factoring 5x squared plus 36x plus 7. This is no longer an x squared, so I'm not trying to find what 2 numbers multiply to 7 and add to 36, because that's not the result that gets me the factorization. One of these numbers in the x squared, it's not x times x anymore, it's going to be a 5x times x. Assuming there's no GCF, and there isn't, I can't factor a 5 out of any of my terms. So I know that in this particular situation, because like they have it kind of written differently, but when I'm spelling this out, I would begin by saying, I know that if this is factorable, this is how I'd begin. A 5x times an x. Now, everything's positive here, so I know that these will also be pluses. But 7 also being a prime number, just like 5 was, I know that this is either going to be a 7 and 1 right here, or this will be a 1 and a 7 right here. Now, they're different in this case, though, because when you FOIL, the outside or the outer terms added with the inner terms, look at how 5x multiplies with this term. If I had a 7 and 1 here, that would be 5 plus 7. But if I have it the other way, this will be 35 plus 1. That totally changes the result. Now, the end goal for this is to come up with your factors of your first and last terms until you find which one gives you the middle term through addition. So if we go back to the one that I just put in to start with 7 and 1, like I said, you'd have 5 plus 7. The way that they say 7x plus 5x to give you 12x. When I say 5 plus 7, I know that these have x's there. I know they're going to combine. I care more about the numbers than having the x for the sake of what I'm testing. So when I say 5 plus 7, I mean they're 7x plus 5x. They get 12x, I get 12. That's not 36. But when we switch them, 1 and 7, we get 35 plus 1. 1x plus 35x is 36x. 36 was the value that I'm looking for. If that's the value I'm looking for, that's the factorization of the problem. That's the answer. They wrote the same thing down here in reverse order. Like I said, I have a little OCD bit where I write the bigger term first. I think it looks better to me. It's just part of my testing. So if I ever have something different from an answer key, it's just because the things are actually swapped. But it's the same answer, the same tests. Now, I knew that with 36 being so big that it's worth putting the 5 with 7. So I probably would have only tested that one first or considered it, and that ended up being the answer. Now, some of these problems end up getting a little bit more difficult. Reason being, not all sets of numbers are prime. They can be composite, which means we're testing more factors. But sometimes they're actually pretty nice. So 3t squared plus 16t minus 12 for number 25. We're going to go ahead and factor this thing. This is where it is important for us to look for GCFs of any sort. I'm looking at all the problems. None of them have GCFs. I really wish that they had some. Like, could you factor a 3 out of all the terms? You can't seem to here. Again, the review's limiting a little bit of what the rest of the problems showed you before. That's okay. What I do know, though, is that if this is factorable, 3 being a prime number means that this will be some 3t times t. It has to. It has to. 12 is not just 12 times 1, though. 12 comes from 12 and 1, 6 and 2, and 4 and 3. Now, there's a reason how I know which one that I'm going to kind of pull this out from. I will consider all the tests for you, and then I'll talk about that after, and I'll show you what it looks like. The other thing I wanted to mention is this whole negative product means one is positive, one's negative, and I don't know which one yet, compared to the last set of problems where it was always an x times this and x times that. I always knew that the bigger number would have been positive for a positive sum, and the bigger number would have been negative for a negative sum. But now that a number is going to be tripled, and we don't know the sizes of the numbers quite yet, you're not quite sure which one they go into. But what we do know is that when you add two numbers up and get some result, that switching these signs would just get you the opposite result. Meaning, if I test a value set through this plus this and I get negative 16, I'm just going to switch this plus and minus around, and then I'll get positive 16 out. So what you're doing is you're testing by saying, let's plug 12 and 1 into here. I'm going to give all the reasons why these would never have worked before. But I'm going to try and put 12 and 1 here. And I'm, because those are factors of negative 12 like that. And I'll get negative 3 plus 12. Again, that's negative 3t plus 12t. But negative 3 plus 12 is 9. 9 is not 16. Those are not the numbers. At least that's not the order. How about we switch it? 1 and 12. It's a viable version. Still not one I would have tested for two reasons. I'll tell you why for both later. Is negative 36 plus 1, which is negative 35. Again, even if it were positive 35, it's still not good enough. So it's not about the signs. It's about the values. Let's try 6 and 2. Not one I would have tested again for a different reason. And we get negative 6 plus 6, which is 0, not 16. That doesn't work. Now let's try 2 and 6. And we get negative 18 plus 2, which is negative 16. Now, I wanted a positive 16. Does that mean that these are wrong? I mean, it's not perfect, but these are the right numbers in the right spots, just the wrong signs. So let's turn this into a minus and this to a plus, and if you'll notice here, now you will get 18 minus 2, which is 16 indeed. So this is the factorization. Once you find it, you don't need to test other things. Notice I didn't test 4 and 3, or 3 and 4, whichever way, and I wouldn't have to begin with for different reasons. So I'm going to talk about my strategy a little bit. It might help speed up the other problems, so I just talk more of my process, weed out the problems the values I never would have tested, because there was only one number I would have tested in all these, or one combination out of the 6. And let's talk about it. So what makes all these other ones kind of wrong? I'm going to bring them back. And remember, I'm not talking about the plus and the minus part. I'm just going to throw those in like that, and then hopefully it kind of makes sense. I'm going to explain why none of these would never have been considered for me. Give me 1 second. Any reason I can come up with. Give me 1 moment, sorry. I keep writing a 3. I should just pause this and come back. In fact, I will. Give me 1 second. Okay, I've written them all. Okay. So there were 6 different combinations we could have tried. This is the one that worked. These were the ones that would not have. Notice that 12 and 1 switched here. If I switch 6 and 2, I got the right answer, but this is the one that didn't work among them, and switching 4 and 3 are here. Now, excuse me, The book probably would have showed what they are just to land on it. I think it's an important thing to try and do. But remember, once you find your answer, you are done. But why wouldn't have I ever tested these? Let's start with, I guess, the top. And I'll mark other ones that have the same issue. 3t plus 12, if you notice, has a GCF of 3. That means that if I factor this completely, it would actually turn into 3 times t plus 4 times t minus 1, which means that this whole polynomial would have had a GCF of 3. Well, this didn't have a GCF of 3. It might have in the first and last terms, but 16 doesn't divide by 3. So why would this have a GCF of 3 in the factorization and factor even more to this when this doesn't have a GCF of 3? And the answer is it wouldn't. So if it wouldn't have a GCF, then you can't put in numbers with other numbers that would present a GCF. This doesn't work because there is no GCF. This shows a GCF, but there isn't in the original problem. That's why that wouldn't have worked. No GCF. There are other reasons that I'll get to. This version would have been fine when it comes to GCF setup. The 12 is no longer with the 3. However, I'm trying to get to the number 16 out of this, and I got to multiply 3 with 12, while the other one just multiplies with 1. I mean, I know I'm going to get a small result from that, but this number's too big. Negative 36, I mean, despite the fact I'm telling you the calculation right now, is a little too much information right now. When I start to consider what numbers to put in, I know I got to get to 16. 3 times 12 is just too big. It's too big calculating-wise for me to get back to where I want to get back to. Now, this third one is actually pretty good for a different reason that we'll talk about that shows why none of these other ones would have worked, that I never would have even talked about these to begin with, but I wanted to bring up why these also wouldn't have worked. But this wouldn't work because of a GCF issue, because 3 and 6 both have a GCF of 3. There's no GCF in the original problem, once again. That's the one reason why I never would have tried that one, and I only would have tried this one. This one also has a GCF issue down here with the 3 and 3, so I'll just present that right now. No GCF there either. Now, why wouldn't have I tested this one? It's actually viable as far as GCFs, as far as too big or too, well, maybe not too big or too small. I see a negative 9, and I notice this is going to be there. So maybe I can say too small. That's fine. There's another problem with this one. Let's look at what these numbers would have added to here, 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 and here. These numbers would have been, whether positive or negative, the difference of the numbers would have been 9. So like 9t right here. Let's look at just the 9. 9, negative 35. Again, doesn't matter positive or negative, but negative 35, negative 5, and negative 9, I think. If I did something wrong, I apologize. But there's something that all of these have in common. These numbers are all odd. They're all odd. Now, when you look at this one here, or our answer of 16, but this one added to 0. 0 is actually an even number, and these are odd. Now, is that just coincidence? Did I know this was going to, or did I know it was going to happen beforehand? The answer is I knew this was going to happen beforehand. And the result is, or the reason is because we are adding an odd number with an even number with an odd number, an odd number with an even number, and an even number with an odd number. Odd plus even equals odd. However, with using 6 and 2 as factors, both even numbers, when you multiply by any integer, odd or even, you will always get even out. This would have been an even plus an even number. This is an even number plus an even number. And 16 was an even number. So why don't those other ones work? Because we chose factors of 12 where one was odd, one was even. And when pairing it up with only odd factors out of 3, you are only going to get an odd result. Odd, 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 odd. And that's why this one wouldn't have worked. Besides maybe being too small, odd is the reason. So this is the other, I know I'm spending a long time on this problem. I want all the other ones to go super fast when I talk about these things, because I'm going to do a little bit more than the book does when it comes to strategy. And obviously I talked about these in previous videos and stuff. That's why those videos went very long. So for this one here, I never would have tested 12 and 1. I never would have tested 4 and 3. Only odd results would have come out. I only would have tested 6 and 2, but I wouldn't pair up the 6 with the 3 because of GCF that never existed. The only one that was possible was negative 2 and 6 or positive 2 and 6, negative 6. And all I would have to do is switch signs once I figured out which one was which. So that's number 25. Now I get to go faster on all the other ones. There are no GCFs, as I mentioned before. Well, actually, take it back. This one has a GCF of a different ilk. Number 26. Negative 5y squared minus 22y minus 8. Let's factor. Now, for these problems, you do want to factor out the negative of a leading term. I couldn't care less what other terms were negative, even if these were all positive. I couldn't care less if they were negative or positive. The leading term was negative. We must factor out the negative. Besides the fact that it is a way of completely factoring your problems, it also makes this so much easier. I can't sit around and talk about why without spending like numerous examples and problems. It just makes it so much easier. Not only does it make it so much easier, but it makes it more likely you'll be correct. I think I'll just say it that way. You might not know something's easier or harder and just say, oh, look, I did it just as easily. No, you probably got it wrong if you didn't factor out the negative. But here's what I do know. With the negative factored out, it'll stay factored out. And now that I have a positive 5y squared, I know that's going to come from 5y times y. Everything else in here is a positive, which is cool. I know I'll have pluses and pluses here. Now, 8 has factors such as 8 times 1 and 4 times 2. Like I just mentioned before, though, with this being an even result of a sum, 8 and 1 will not work with pairing with odd factors that are 5 and 1. Only 4 and 2 are possible. Now, either here is conceivable putting 4 and 2 or 2 and 4. Both would give you different results. But knowing I need to get to 22, I probably want to get bigger first. So 5 times 2 might not fit the bill. I might have to multiply the 5 with the 4. That's my first test and what I want to do. You can choose either or. It's not going to take too long. But here I get to do 20 plus 2. That'll give me 22. Notice if I put 4 here and 2 here, I'd have 10 plus 4, which is 14. Not bad. It's just not the first one I'd test. 22 is kind of a large number coming off of only multiplying 5 with something. So I wanted to multiply 5 by the biggest number possible. And that's it. So the negative factors out of there. This is the complete factorization of this guy, and I am finished. Much faster than the other set, but then again, I can go even faster, in my own head. I just want to teach to you what I'm talking about. Number 27, we have 6x squared plus 17x plus 7. So 6x squared, whoops, no parentheses. 6x squared plus 17x plus 7. Let's factor. Now, 6 happens to be a composite number, which means this can either be 6x times x or 3x times 2x. I tend to go with the 3's and 2's more so. I don't know what the answer is. If I work it, I just found it out in my head. I was going to say if I work it out enough in my head, then I'll probably just land on it. And the pluses, by the way, for these. I don't know which one's which, and furthermore, because it's an even and odd, and even and odd, and the result is odd and all that stuff, I can't talk about the even odd stuff here this time. That's not going to be really a part of what this one's going to be. It's always going to get odd results no matter what's here. Furthermore, no GCF issue things. This one's just more of a matter of testing. This is where you can weed out some things that might be too big or too small, depending on what's there. For example, I am not going to try and multiply 6 with 7 and get the answer of 17. So I'm going to leave that one out. I can leave this one in here and test it. That's fine. Same thing with 3. 3 times 7, it's not massive, but it is more than 17. So I am only going to test this one here as well. So let's try these. 6, just by the FOIL portion, we do 6 plus 7, which is 13, not 17. And here, this is going to be 3 plus 14, which is 17. So that one ends up being the bit right there. Hopefully you know what I'm doing with that. This isn't foiling everything. This is just the outside plus the inside, not even including the x's. I'm just trying to get my 17 by doing this times this, plus this times that. And this is the factorization, not this guy. But I tested it. It was a valid test. And only testing 2 things mentally, much less, is fine. Testing 12 things, even if mentally, is not. Not for anybody, not even for me. If I have to test that many, I'm not saying it's an invalid problem. It's just, it must be a big problem. It must have been a big problem because I have strategies that take me out of the way of that. All right, negative 2y squared plus 7y minus 6. I can factor a negative out of here, just like the number 26, I believe it was. And every sign will change inside of it. Make sure you do write them as the signs change first, because now we're dealing with this here, not with a negative 6 and a positive 7, but a positive 6 and a negative 7. Now, 2 is a prime number. We get 2y times y happening here. I have a negative sum with a positive product, which means I will have minus and minus. 6 I mentioned before is 6 times 1 and 2 times 3. Anything here is potentially valid. However, I will not pair up. If it's 6 and 1, I will not pair the 6 up right here. And if it's 2 and 3, I will not pair the 2 up right here. 2 cannot have a GCF of 2. Excuse me. These cannot share GCF if this originally didn't. So the only possibility is by flipping those over of 1 and 6 and 3 and 2. If I try 2 times 6, I'm going to get a number too big, so I'm not going to try testing any more of that. I'm only going to try 3 times 2. I get negative 4 minus 3, which is negative 7. I only tested one set. There were only a couple things to test, but I only tested one thing, and that was the result. Remember to keep the negative factored out. And also keep in mind, I'll do it on the last problem, I guess, but they are not having us set it equal to 0 and solve in these problems. They really should be. I mean, yeah, they have 6 problems to give us. Why not make 2 or 3 of them equal to just one of them? No GCFs outside of negatives either. It's kind of interesting how they go about some of the review things. It's just I question it. I do, and I'm teaching it. So no GCF once again, although 9 can divide by 3, 26 can't, 27 could have, but it's a 26. So here we have 3z and z with this guy. Negative product comes from a positive and a negative. This is the first time in a long time that we've seen two sets of odd factors here. And yet, and I'll show you how I know there's only one answer with this, but 2 sets of odd factors here, and yet, well, sorry, 2 sets of odd factors with no GCF or whatever, because we're going to get an even result. We're only going to get even results. It's always going to be an odd plus an odd. But the nice thing about this is that 9's factors are 9 and 1 and 3 and 3. Listen, I can't put 3's here because I'd have a GCF there. And I can't put 9 here. Whoopsie. And I can't put 9 here because, whoops. I can't put 9 here because they would have GCF. So I only have one possibility, which is 1 and 9, like that. It's the only possibility. Now, I might have to switch the signs if the answer's, whatever. So negative 27 plus 1 is negative 26. Boo hiss, I got to switch the signs. And we'll put a minus here, plus here. So we get 27 minus 1, which is positive 26. This is my only option. And that's the answer. I don't know if I'm still linking them. I guess I can here, but there's a factory video that I made that has more different types of factoring than even we've seen. Not until you hit IM3 will it make sense, but how fast I do problems like these is something to, I hate to gloat, like something to be impressed by, in that, like, I'm going to say, hey guys, look at me, I'm so fast. It's like, hey, look how fast you can be. That's the point. Efficiency matters. I mean, it does. Now, I will be doing an equals 0 version of this on the side, equals 0, to solve that after. So we'll go and do that. 10a squared can come from 10a times a, or 5a times 2a. Now, again, I don't know which one's which. I'm always going to get odd results from no matter what I do. Thankfully, 3 being a prime number means that, it can either only be one of two things, 3, 1, or 1, 3. Now, this is the kind of problem where all of these could have been valid tests depending on the size of the numbers, but no GCFs, no even odd issues. I'm trying to think if there's anything else I want to say. Yeah, no GCFs, no even odd issues. So anything's valid for testing. Now, I'm getting negative 13, so I'm not going to try 10 times 3, so I'll get rid of that. 5 times 3 is pretty close, but actually 5 times 3 is pretty close. I'm going to leave that one. I think 5 times 1 might be too small, in fact. But, okay, I'll test these 3. I'll test these 3 sets right here. Let's start with this. Negative 10 plus 3. Not negative 13. That's negative 7. But kind of a valid test, but it's not going to work. All right, let's try these ones. Let's try 5. Let's try 5 and 1. Negative 5 plus 6. That's 1. Now let's try this last one. Negative 15 plus 2. Okay, it's negative 13. So it ends up being that very, very last one. We're going to get 5a plus 1 times 2a minus 3. Now let's do the version where it's set equal to 0, and let's solve this thing because the answers are not negative 1 and positive 3. Instead, when it's set equal to 0 in this case, we still set those two individually equal to 0, but there are 2 steps to solve. It's not just subtracting 1, but either 5a plus 1 would equal 0, or 2a minus 3 would equal 0. So we subtract 1 from here, and then divide by 5. You get this fraction of negative 1/5. Remember, we're trying to find the value that would give us 0. And then here we get 2a equals 3, and a equals 3 halves, like that. So those are the 2 different options of possible answers that you would get from that set. If we were solving using that stuff. Okay, let's move forward to section 2.7. Factor each polynomial. Now, these are those special case polynomials, meaning they are either a difference of 2 squares or a perfect square trinomial set. There may be GCFs. I have no idea. Based on the previous problems, probably not. But if they aren't in standard form, I'll put them in standard form, even if it means I have to factor out a negative after. We'll see. So the two examples that they give you for a difference of two squares, x squared minus 16, we recognize it is an a squared minus b squared scenario, which means it factors into the a plus b times a minus b that we distributed out of previously to get into a setup such as this one. So knowing that that goes into that, a plus b times a minus b is kind of a big deal. Also this one, recognizing a perfect square trinomial when you see it. See, once again, we're seeing this in a vacuum. You know this is out of section 2.7, so you know these are special cases. But can you recognize that 25 is a perfect square of 5, and x squared is a perfect square of x, and 9 is a perfect square of 3? That's a good setup in going, hey, maybe this is a perfect square trinomial. If only the middle term is double the product of 5 times 3, those perfect square, those square root values. And yeah, 30 is double the product of 5 times 3. 30 is double the product of 15. So this ends up being 5x is squared, 3 is squared, and this is double 5x times 3. It is subtracted, so we are going to have a subtraction here in the answer with 5x minus 3. You could factor given the other methods we talked about before, but you'd have to consider the fact that 25 and 9 are not prime numbers. They are composite, which means there are more tests to be had. Maybe I would test 5 and 5 and 3 and 3 first anyway, instead of 25 and 1 and 9 and 1 and things like that, but maybe not. So it just depends on what the problem is. All right, let's go on to number 31, x squared minus 9. Let's factor. So we got to recognize that this is x squared minus 3 squared. I mean, off the bat, it is one of the only quadratics they ask you to factor that doesn't have a GCF with an x. So it looks like a difference of two squares. I mean, that's one you're going to have to note. But the question is, can you recognize what those things are that you're squaring? And can you write them out in their factored form? So that's really what you're trying to go for. Recognizing it for what it is one thing. Factoring it's the other. That's number 31. Let's go to number 32. Once again, the same thing. I'm recognizing a difference of two squares. Literally, it is a subtraction of two terms, and those two terms are both perfect squares. Y squared is squaring y. 100 is squaring 10. This will become y minus 10 times y plus 10. And it doesn't matter which one you put first for the minus and the plus. That's why I intentionally swapped them to show you that either or is fine. Number 33, I do have three terms once again, and they're asking you to factor. It is not incorrect to factor by conventional means, meaning with a 1z squared, asking yourself what two numbers multiply to 9 and add to negative 6. But the sake of the fact of the matter is it'll be the same number twice. It'll be negative 3 and negative 3. But if we treat it like they're asking us to, z is a perfect square, z squared is a perfect square of z, 9 is a perfect square of 3, and we are doubling that z in that 3 to get our 6z. That's where that's coming from. Because this is a subtraction, this will end up being z minus 3 quantity squared. That is the perfect square trinomial version factored. Remember what I said? Negative 3 times negative 3 is 9, and negative 3 plus negative 3 is 6. That's also written as z minus 3 times z minus 3. But, of course, when condensed, I guess more so, in that form we get this, which is important for later measures of what we do in future chapters. Number 34, we have m squared, and as you notice, none of these are set equal to 0 to solve. I will not set this one equal to 0. M squared plus 16m plus 64. One more time, it's one of those things where m is being squared here, and 8 is being squared here, and this is double 8m. This does become m plus 8 quantity squared, if you recognize a perfect square trinomial for what it is. The last section is 2.8, and they give you a nice bit of examples to do as well as problems, and they let us solve here, which is nice. Maybe that's what they were saving us for, solving at the very end. I would have liked to solve beforehand. I imagine this is where we're also going to get some GCFs, because they just talk about factoring completely. They say everything is thrown under the rug here, or on top of the rug. Yeah, everything is thrown out for us to do, including a new thing called factoring by grouping, and I'm sure that that'll pop up with the first problem that I look at right here. So in standard form, or at least, yeah, you want standard form. In standard form, if we pair up terms, well, they show you, if you pair up sets of terms in a factorable case, what we're looking for, you should be able to find a GCF of the individual bits, such as these both have a GCF of x squared, and these both have a GCF of negative 3. When you factor those two things out, you'll notice that you'll have the same common factor quantity that exists in both, if you indeed found the GCF of your paired up sets of terms. And when you factor that actual x plus 4 quantity, and I do it in my 2.8 video, so I'm not going to kind of talk about it more, but if you factor x plus 4 out of both of those sets, you'll notice that that part can kind of go away here, and you'll be left with x squared minus 3 in the other portion of this. And that is the complete factorization of this cubic quadrinomial. Now, that being said, sometimes there's more to factor, such as the x squared minus 3 could have been a difference of two squares, and you would keep going. Or there could have been a GCF to begin with, and I should have factored that to start off with, if so. Okay, next one, part B. We do have a GCF to begin with here, with a 2x squared out of both terms. Then you're left with x squared minus 4 inside, which we would have been done if this wasn't a special case of, once again, a difference of two squares. So we're no longer in the section of what's a difference of two squares, what's not. Here you'd have to recognize it. X is being squared here, 2 is being squared here. That leads to an x plus 2 times x minus 2, with 2x squared still being factored on the outside, on the outside, on the outside. So that is the complete factorization of this polynomial, the quartic binomial. And the last example, 2x cubed plus 18x squared minus 72x, I am clearly seeing a 2x GCF out of all three of these. We really want to factor out that x, but that 2 will help make things a lot smaller. You have x squared plus 9x minus 36, which if factorable, we keep factoring down, and it looks like it is. 12 times negative 3 is negative 36, and 12 minus 3 is 9, with these both being 1x's. It's one of the basic factors, with the 2x still on the outside. If it wasn't factorable, you just leave it. And that's what it would be. Not everything will. I don't know what will here. We'll take a look. Let's start with number 35. N cubed, factor completely, n cubed minus 9n. I see a GCF of n. I see a GCF. I see a GCF of n, and you're left with n squared minus 9. Now, that can factor further, because that's a difference of two squares of n minus 3 times n plus 3. And that is the final factorization of number 35. This is where I will go a lot faster with all the other factorings because we've done them. Basically everything outside of maybe factoring by grouping, which looks like what number 36 is all about. So at number 36, we have x squared minus 3x plus 4ax. Whoops. Let's do that again. Plus 4a. Yeah. Plus 4ax minus 12a. Now, I'll have you know that although I could factor by grouping right now, for the sake of other problems where you can't with a disarray of items, it's worth your while to check and consider whether to see you are in standard form or not. This is degree 2, degree 1, degree 2, degree 1. So technically it's not in standard form. Doesn't mean it won't work for what they gave us, but if they put this wouldn't work. And this is still degree 2, 1, 2, and 1. X squared needs to be at one end, negative 12a needs to be at the other end for this. Not necessarily ends, but they need to be paired up with other sets of guys. So this would have worked, but I'd rather put it in standard form, just because there's a case where you might not be able to, like I just showed. So instead, I'm going to do it to guarantee that it will work. Now, there's still a specific order that we do standard form. If we're treating x as the, actually, I always say go with what's alphabetically first, right? Let me not even do this standard form like this. The alphabetically first variable should be the dominant one. So you know what I'm going to make the dominant one? A. So let's go to the degree 2 term that has an A in it first, and then I'll go with one that doesn't. This will still work. It'll still work. And then I'll go with the degree 1 term with A in it, and then the degree 1 term without it in it. This will still work just fine. But I wanted to follow my own basic instinct on that. When I said standard form, I got to go by the letter of how I call standard form. So we got to find a GCF of both of these terms right here, which is x. X can factor out. You're going to be left with a 4a plus x inside. I can factor out a negative 3 from this set here, and I'll be left with, once again, factor out a negative from these turn positive. Negative 3 times what is negative 12a? 4a. Negative 3 times what is negative 3x? A positive 1x. So if you notice right here, 4a plus x is a common factor from both of these, the x minus 3 bits. If I factor 4a plus x out of both terms, I will be left with x minus 3. as a result of that. And that is the final factorization. Now, there's more than one version, more than one way this will be written as an answer, but the fact of the matter is this is what you'll get. You might see it say x minus 3 times x plus 4a. It's still the same thing. Nothing changed. But yeah, that ends up being it. All right, let's move on to number 37. So hopefully we get to factor by grouping at least one more time. It looks like on number 40 we will. Maybe even on 41, depending on the word problem. Number 37, we have 2x to the fourth plus 2x to the third minus 20x to the second powers. I have a GCF of 2x squared that I can pull out of here. 2x squared times 1x squared is 2x to the fourth. 2x squared times 1x is 2x cubed. And 2 times negative 10 would give us negative 20, and the x squareds just are what they are. And we are going to keep trying factoring here if we can. I don't believe we can. This is a 1x squared, so I got to find two numbers that multiply to negative 10 and add to positive 1. 10's factors are 10 and 1 and 5 and 2. 10 minus 1 is 9. 5 minus 2 is 3. You don't get 1 from that. So this is the complete factorization of this. We are done. Unless I screwed up a GCF thing, which I didn't, and I didn't copy the problem down wrong either. And that's it. So you don't just pull and factor things just because. If they factor, you do it. If they don't, you stop. Number 38. 4 more problems to go. Number 38. Now we are going to solve. So this does get into that heap of everything that I mentioned before, saying why aren't they having a solve? We'll get to solve here. It's just that we're saving it till the very end. So I do see a GCF of 3x. You definitely want to pull out that 3, but you definitely have to pull out that x. I'll have x squared here minus 3x, 3x times negative, and then minus 18. 3 times 18 is 54. Now, as far as solving this goes, remember this can still factor more so, or if it couldn't, then you wouldn't have means of solving at this stage in your IM2 learning. So we keep going. This will be some x times x bit. The two numbers that multiply to make negative 18 and add to make negative 3 are negative 6 and positive 3. And now we have our product. This times this equals 0. 0 product property. That's what we're going for. If 3 times x equals 0, then x would equal 0 when you divide both sides by 3. If x minus 6 equals 0, then x would equal 6 when you add 6 to both sides. And if x plus 3 equals 0, then x would equal negative 3 when you subtract 3 from both sides. This cubic had 3 solutions to it, and we've cracked them all by factoring. Starting with that GCF, that really helped a lot. Number 39, 16x squared minus 36 equals 0. 16x squared minus 36 equals 0. Off the bat, it is already a difference of 2 squares. Maybe you notice by it being 2 terms. Maybe you notice because the 16 and 36 and all that. So it is a difference of 2 squares. This would be a 4x plus 6 times 4x minus 6. But as you probably notice within, and there's nothing wrong with this, but as you notice within, well, there is if I ask you to factor completely. I'm asking us to solve for x. If you notice, both of these have GCFs of 2, though. These also shared a GCF of them together. So here's one way they could have told you to go about it. It's not wrong. But I'm going to start with GCFs as I generally do. Factor a 4 out of all this, and you're left with 4x squared minus 9 equals 0, which is still a difference of 2 squares. And here we have 2x plus 3 times 2x minus 3. Notice how 2's could have factored out of both of those. 2 times 2 is 4. Now this 4 does not have anything to do with equaling 0. 4 times something equals 0. There are no x's outside of here. This has nothing to do with it. I could divide both sides by 4. I could say either 4 equals 0, which is impossible. But the fact of the matter is, introspectively, only 2x minus 3 times 2x plus 3 are the only parts that I care about when it comes to solving for this. Sorry, something popped up in my screen. It was a really, it kind of scared me. It was a my phone when I get text on my phone, I get notifications down in the corner of my screen, and someone sent an image. It was one of those clip art things, but it was like a big face, and it scared me. I'm like, why am I getting a big face popping up? Anyway, remember, I couldn't divide 4's out of expressions. For these problems originally right here, if there was a 4 on the outside, the 4's got to stay on the outside. You cannot get rid of it. But this is an equation, and I'm trying to find what values of x give me 0, and 4 had nothing to do with it. 0 times 4 is still 0. So here, if I subtract 3 and divide by 2, I'm going to get negative 3 halves. But here, if I add 3 and divide by 2, I get positive 3 halves. And leave them as fractions. I don't want 1.5, negative 1.5. Neither would a book. Neither would a teacher. Now, if I got, because here I'd get -6/4 and +6/4. Oh, you better reduce those. So that's where I'm saying that, like, you'll get the same answer, but you better reduce them. You divide both of those by 2, right? So you'd still get the same answer. Just really keep that in mind. Just do the GCFs first. If you got to do it in factoring problems, do it here. That's the Robinson way, right? All right, number 40, z cubed plus 3z squared minus 25z minus 75 equals 0. No GCFs for all of the terms, but because it's the 4-term set, this is factorable by grouping. By the way, not all problems with 4 terms are factorable by grouping. It's just that they're not going to give you one that's not, because you wouldn't know another method until you hit IM2 or pre-calculus or whatever. So just be aware of that these will be factorable by grouping. It's in standard form, which is also another good set here. Z squared can factor out of the first 2 terms where you have z plus 3. And you got to factor the negative out of here. Not only does it make it a leading term to factor out of, but if you got to get z plus 3 inside of here. And factoring out -25 is going to do exactly that. So when you factor that there, you can turn this into z squared minus 25 times that z plus 3. Z squared minus 25, z plus 3 factors out of both terms. You got that. And z squared minus 25 is a difference of 2 squares, which factors into z minus 5 times z plus 5. Again, something you're going to have to notice on your own. I mean, obviously, we come to the case of needing to solve for this thing. So you're saying, well, gee, they better let me factor it. So and they did. So z equals 5, z equals x, z equals -5, and z equals -3 in that cubic. Okay. Last problem to go. We're almost done. We'll finish within the hour and a half. Number 41. Whew. Now keep in mind, I also led example problems, right? Let me count, actually, I'll finish in the hour and a half, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 plus 41 is 53. I would have covered 53 problems in 90 minutes. That's less than 2 minutes a problem. When people say that my videos are too long, I ask you, how long would it take you to do the 41 problems, not the 53 as well, with the explanations? I don't know. So for those who complain it's too long, find another channel, or fast forward or whatever. I'm trying to teach. Number 41. And by the way, I'm not saying that people in comments say that they're too long. Sometimes my students say it's too long. I say, shut up. I do. I say, fool, shut up. Be gracious. Better than being fast and you not getting it. A box, if I talk too fast, I get it. A box in the shape of a rectangular prism has a volume of 96 cubic feet. The box has a length of x plus 8 feet, a width of x feet, and a height of x minus 2 feet. Find the dimensions of the box. So a box, if you like, when in doubt, draw it out. I don't know if that's a phrase I've been able to say to you guys quite yet, but it's something for word problems that you'd want to do if they don't have a drawing. A box, 3-dimensional rectangular prism, just like this. 96 cubic feet is the volume. Yeah. And we have an x plus 8 length, an x width, and an x minus 2 height. The volume is a length times width times height scenario. So we will set this length times width times height equal to 96. I'm going to write it in kind of a clean way. I want to write the x first. X times, boom, x plus 8 times, boom, x minus 2 equals 96. So that's our volume setup. We're going to solve for x. Now, it is not, first of all, it's not this. It's not x equals 0 or x equals -8 or x equals 2. Don't forget that this is equal to 96, not 0. So then don't say, oh, well then in that case, x equals 96 or x equals 90. No, it's not like that. Zero product property only works for 0. We got to set this equal to 0. We have to subtract 96 over. But 96 will no longer then be a part of the factorization of this whole thing. We need to multiply this whole thing out, then bring 96 over, then factor it with 96. We'll have brand new factorizations with this afterward. It's not going to be the same at all. So we have to see what's going to come up as a result of that. So we start by foiling. And FOIL by distributing. And to distribute, you don't distribute everything at the same time unless you clearly know how x will increase the degrees, but start with the foiling maybe, then bring the x in afterward. So this will be x times x squared minus 2x plus 8x, then minus 16. And then I distribute the x in here. Like I said, it just increases the degree of each individual term, like that. Not x squared, just x. Equals 96. And now I can subtract the 96 over and feel kind of comfortable with what I have. Minus 16x minus 96 equals 0. Now I have something where it's 4 terms and all that, and no GCFs within here, but I can factor by grouping, right? That's going to be that next stage. So I'm finding the GCF of x cubed plus 6x squared, which is x squared, left with x plus 6. I hope that here I'll have an x plus 6 after I factor out the proper thing. If I factor out a negative 16, would it do it? Sure, negative 16 times x is negative 16x. Negative 16 times 6 is negative 96. So that does bring me to that portion. If I factor out the x plus 6 from both of these guys, I will have x squared minus 16 remaining here. And if you recognize, what do we have? A difference of 2 squares, which is x minus 4 times x plus 4. So if you notice, this is a way different factorization when you subtracted the 96 over here than we had here. Way different solutions. So now my solutions are either x equals 4, or x equals negative 4, or x equals negative 6. However, this is a word problem, and it wasn't just solving for x, it was find the dimensions of the box. X was one of the dimensions, x was the width. Then there's an x plus 8 and x minus 2. If I substituted negative 4 for x, I would get negative lengths for 2 of the 3 of them. And x minus 6, I would get, for 2 of the 3 of them. That doesn't work. But 4 seems to work out there for it. And the width would then be 4. 4 what? 4 feet. The width is 4 feet. Let's put an equals. The length is going to be 4 plus 8 feet. 4 plus 8, which is 12 feet. And the height is going to be, I think, minus 2. 4 minus 2, which is 2 feet. So those are the dimensions of the box. So 12 feet by 4 feet by 2 feet, however you want to put it. That all multiplies together to give you 96. That seems to follow along with the representation. And that is a great problem to cap things off of. It kind of shows everything that we had within. And so listen, they use zero product property by the very end. Maybe I poo-pooed on them a little bit for not doing it beforehand. But if in the examples they showed it, and there weren't a lot of GCFs overall, but if in the examples they showed it, then I kind of felt like they were going to do it there as well. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I did finish within the hour and a half. I hope that this was worth your while. If you still want to go back to problems, check the timestamps in the description section down below. Go to the playlist if you want to find other things on 2.1 to 2.8, including the quiz things from before. My next video should be the Chapter 2 test and cumulative assessment. Check out that factory thing as well, just to see the speed of some of the ways that I factor on problems. Factoring by grouping is going to be in there. The advanced quadratic factoring and special cases. There's another set using what's called rational root theorem, which you'll have no idea what that's about. You should probably skip those ones if they show up. Anyway, guys, that'll do it for me. This was an awesome video, or this is an awesome timeout for you guys. Thank you so much for watching, and take care. I will see you in the next one.